My name is Chandler Gruner. I'm an Extension Soil Health Specialist located in Minot, North Dakota at the North Central Research and Extension Center. And today I'm going to present you a little bit of information about soil health matrices from a soil structure perspective. So we're going to start with a little bit of brief history on soil health. So it's not really a new concept in terms. Some over the years, it's kind of varied a little bit in terms of different ways people have called it. Soil quality has been a common term for the last 20 plus 30 years. And then a common theme with other terms in soil quality is soil conservation and soil protection. So that's the heart of most groups that are advocating for this. And so the groups had the similar fundamentals and they didn't describe it in the same way, but they had the same ideas. And so some of these are no-till alliances, zero-till alliances, cover cropping groups, diverse rotation groups, all with the heart of keeping soil conservation and protection in mind. So in 2001, I pulled the definition of soil quality was defined by the USDA as the capacity of a specific kind of soil to function. So more recently, soil health has become a term like the title of my job, being a soil health specialist. So soil health has been defined now as continued capacity of a soil to function as a vital living ecosystem that sustains plant, animals, and humans. So the USDA kind of updated the definition, updated the terminology to more current wording, and then added a few more items and elements to kind of fill out that definition. With this expansion of the definition, we also have seen an expansion in the sampling as we included more elements of like animals and humans coming into this aspect, and plants too, beyond just the basic soil that was originally included. And so how do you achieve these principles? So looking at this picture of the soybean field on your left-hand side of your screen, so this is a no-till soybean field that used a cereal rye cover crop. You can see kind of below the soybeans there at the bottom. And so this producer wanted to minimize disturbance by going with no-till. They maximized the living root by having the cereal rye grown in the fall and the early spring prior to soybeans. They maximized having that soil covered, so once the cereal rye was terminated, it fell down. The soybeans started growing up, and then in the next fall, they'll have another cover crop that'll come up. And then they also maximize biodiversity just a little bit by having cereal rye and soybeans instead of just the typical monoculture where you only have the cereal rye or only have the soybeans and then the cereal rye, having two things instead of just one in a year. So on the right is these principles laid out by the USDA in this nice little infographic. So soil health parameters, they're made up of indicators, and so we talk about the indicators of physical, biological, and chemical. So the majority of my presentation today will be focusing on the physical properties, but you can't ignore the other two. It's like a tricycle. You need all three tires to help keep the balance. And so chemical primarily can be thought of as nitrogen, phosphorus, potassium, and other nutrients in a cycling sense. So just keeping that balance and like the nutrients, like Brady was talking about before with the potassium being mined away. And so returning that potassium back in and keeping it as cycling to keep your plants healthy. Another chemical perspective is reactive carbon, which is measured through POC. And so carbon sometimes put a chemical, but the majority of carbon will be talked about later. And so this is just the elemental carbon that's in the soil. And then there's soil electrical conductivity and soil pH. And so the reason why all these are important is because lack of plant growth or ability to keep the ground covered from salinity, acidity, or pH issues or other issues creates unhealthy soil, unhealthy plants, and no plant production. If you have no plant production, you have no yields. And so soil health parameters is indicators of biological, one of the other three main parts. And so biological parts in the soil are diverse community of microorganisms and macroorganisms in the soil. They can be measured through microbial biomass, microbial activity, like different ones of them can be like PLFAs, other information like soil respiration, mineralizable carbon and nitrogen, soil enzymes, and then total carbon or particulate carbon. Organic matter is another way to look at biologicals, and these are all indicators associated with or direct measurements of biological information in the soil. So the main focus of this talk today will be on indicators of soil physical properties, which can be measured. You can think of like when you send samples to the lab of like bulk density, in-field measurements of water infiltration. Another one you can send to the lab is water holding capacity and wilting point. Soil penetration resistance you measure in the field, and then aggregate stability can also be measured in the lab. So being a soil scientist, we try to think about the importance of context and kind of know what we're going to and what we're going to look at to kind of understand the soil a little bit before we get there or when we're there in the field understanding it. So here's a picture of soil series with the depths on the right-hand side, and you can see there's a little bit different colors, and there's 5 different names here. So these are 5 most common soil series in North Dakota. And so they're just variations, and you can see by different depths, there's different soil colors and different informations, and these letters can indicate back to soil texture changes and structure changes and organic matter changes as you move down and through the profile. So keeping all that information in mind, and so we look at structure. So structure is one of the first principal things I'm going to talk about. Is physical samples may be hard to take, but the direct connection to structure. So here's four soil structures laid out. We'll start with the one on the farthest right bottom. Here's the platy soil structure. So if you think about this platy structure, which is commonly occurring, but if you have continuous tillage and you create a plow pan, eventually this platy structure may form, and then you create a solid plan. The water will not actually go down through the soil, it actually just get stuck and create a pool. What maybe been previously a subangular blocky or a granule structure. The importance of prismatic structure, which is similar to a columnar structure. So if you have a high salinity issues, you can actually, the salts can change the structure of the soil, creating water to flow straight down instead of being able to move around throughout the particles, and it just flows straight out through the profile, not available to your soybeans you're trying to grow on the top. So soil texture was another thing I mentioned in soil series that helps differentiate the layers in different soil series from different places. And so here on the right-hand side, we have a pie chart, and this shows an ideal soil. And so like you see in Brady's thing when he was showing the soil test results, that field there had a 5% organic matter, which is pretty close to what ideally we'd like to see. So 5% organic matter, and then 45% mineral. So mineral is your sand, silt, and clay. So total that makes 50% of your soil being solid, and then the other portion being liquid water, 25%, and air making 25%. And so in this balance here, organic matter is a binding location for nutrients. And one of the important things that you can actually practically change in your field, where your texture that you have is pretty consistent, it's defined by parent material or brought in soil, and so it's not something you can really change. But organic matter is something you can influence as a producer. And so increasing organic matter is important because they create binding locations, and they also for nutrients and for water molecules. And so if you look at this picture on the right-hand side, this is a producer that implemented, he's on a very sandy soil, he implemented some soil health parameters to help to help influence his organic matter building. So the top is a very low organic matter. In the bottom, he's slowly built his organic matter up, and you can actually see aggregates starting to form with these little like pebble-looking things that are in that dish, where the top has very few pebbling and held together particles. And so increasing his organic matter changed his physical makeup of his soil and the function of his soil. And so the little pebble things I was mentioning, they're actually called aggregates. So water-stable aggregates is a method you might see available at some labs to get your soil tested for. So what is that? So that is the connection together of sand, silt, and clay held together, usually through biological and chemical mechanisms. So that's, once again, the physical does not stand alone. You got to know your biological and your chemical properties of your soil as they all work together. So this picture on the right-hand side, I didn't really get a good picture of the hill all the way included in it, but this is a hill that they went out and done some light harrowing on the field. And so prior to the cover crop being established, the water ran down the hill and kind of where they lightly harrowed, moved a lot of the soil. You can kind of see some of the higher organic matter soil pooling at the bottom of the tip of the arrow, and it's going down the field and then washing down through the ditch. And so the soybeans, with being a no-till, they only used a light harrow, so they only had minimum disturbance, and so they only had minimum soil movement. But then the cover crop established, we had a big rain, which caused this event of the soil to come down here in Minot. Bulk density is another parameter that I mentioned. So bulk density is influenced by texture. So sandstone and clay kind of fit together. The particles a little bit different, can influence the bulk density. But the pore space of air and water impacts this the most. And so these plow pans, and so this tillage that we were talking about earlier. And so you can get these compacted layers down at a depth, and it reduces the amount of air and water. So we have that pie chart in the middle again. And so in this case, the mineral and organic matter looks like it increased, but actually what happened is the air and water space decreased. And so you can see in the column on the left-hand side, when you have the air and the water decreasing, you actually limit the ability of water and air to move. So air and water are both important to soybean roots and plant roots throughout the season. So if you don't have the optimal ratios and the amount of water and then roots availability to move through the soil, you'll actually limit the growth and hinder the plants. On the right-hand side, just a visualization of how we take some bulk density samples. This is a split core, so it have a metal sleeve on both sides, goes into the ground, and then we pull it back out. We split the core open. We can divide it by depths to look at bulk density throughout the different layers, and also help identify plow pans if that is an issue, which is not occurring in this soil sample here. So another way to use this as a visualization is um, water infiltration. So if your bulk density is too high and your water can't move into the soil, or you have crusting in your soil, there's some issues that can occur there. So cover crops and then your main cash crop can both add water channels, which helps water move into the soil. So it might be a little bit difficult to see in this picture. It's a little bit easier in the field, but in the middle here, there's a darker blue streak that's going straight up and down. I'm trying to highlight with my mouse there. And so this is where the cover crop was growing in between the two cash crops of the soybean rows. And so the cover crop was growing down and actually creating root channels. So this cash crop has already died. I put blue dye on the soil, added water, and then we watched how the blue dye moves through the soil and found the root channels of the previously existing cover crop. And so if there was a root limiting layer like a plow pan, what you'd see in this dye is it would go down and form a flat horizon and start moving left and right instead of going continually down through the profile. So this is a great visualization to understand how water movement into the soil is impacted by cover crops and other roots. So here's kind of a little bit more pictures of some of that in different soil structure. So on the left-hand side, we have a subangular blocky, so you can see the chunks kind of there, and then water movement in the soil, and it kind of worked its way down around and moved throughout, finding how the grassroots channels goes all the way down. On the right-hand side, I included this picture to show the different cover crop roots. Like some grass species can get 30, 40 inches down, and then alfalfa roots can get down to like 60 inches below. So if you're taking a year off from production before going back into production, you want to grow alfalfa, or you're going to grow alfalfa as your winter cover crop and terminate prior to your soybean production, you can actually get some good root biomass that helps break up layers and moves down through the soil to help that water movement alter the bulk density and add organic matter down to the soil profile. So what's the importance of water holding capacity? So these samples is where you go out, you take a little core, and so you keep this intact core, and then you take it to a lab. AgValue is one of the labs that can test for it, and they'll put in a pressure chamber, and they'll see how much water it can hold saturation, how much it can hold at field capacity, and then you can also get wilting point. So field capacity is thought of as the most amount of water a soil can hold well, after it's had time to drain off. So after a big rain event, you get a bunch of water, your field's saturated, but then after it drains off, field capacity is the water that the particles are holding. So in this picture on the right, we have some aggregate soil, and it's holding water in between them aggregates. Can't see it in real life, but you can see it in a little bit in the soil color there, as it's a little bit darker color from the moisture. Wilting point, so the importance of having cover crops and building that organic matter for water storage is when you're able to lower your wilting point. So that means in a time when you're hitting the really dry point at the end of the season. So in North Dakota here, we have a lot of moisture at the beginning of the season, gets drier towards the end of the season. If we don't have them timely rains, you can have some struggling issues. But if you have a lower wilting point, that actually means the water is more available to the plant at a lower soil moisture, which means they can help scavenge that little bit of water to help finish out the grain fill and pod production for soybeans. So this demonstration I like to do at field days here kind of highlights the difference between tilled field here that had no cover crop on the left-hand side, and on the right-hand side, we've had a cover crop field. And so move the first box here. So we can see in the cover crop field, we poured the same amount of water. We used that device that's sitting in the middle. It sits on top. We put the same amount of water on both of them. They drip through. And on the right, we can see the water ran off the field, some of it, but some of it went through. And the water that ran off actually created a very clear water. Where on the tilled field on the left-hand side, we see most of the water, actually none of it went through. Most of it ran off. Very little came through, but most of it came off. And there's a lot of silt and particles that washed away, losing the soil, which is your valuable resource, kind of going away. So getting a little bit of data that I've collected here. So here's soil moisture data from Minot in the fall of 2024. So this establishment setting it up, we have October to November. So this is right after our cover crop planting. We put soil moisture sensors out. On the right-hand side, we have rainfall from 0 to about 0.25 is the most rain we got in that time period, inches. And on the left is that water potential. So water potential, so the higher you are up in the graph, closer to the top, the soil is actually wetter. And the lower you get, the drier the soil is. And then the lighter colored yellow is cereal rye 6 inches depth of the soil sensor. And then the darker gold color is 12-inch sensor, and then the bare ground accompanying it. So it compare a cover crop cereal rye field to a bare ground field. And so this field was planted with cereal rye this fall. In the springtime, it'll get soybeans to go through the season. And so we're just trying to highlight the story of these two different cover crops growing cover crop growing and not cover crop growing, the soil moisture is actually not statistically different. They're a little bit lower, but it's still within the same realm, and they're bouncing back and forth which one has more moisture and which one doesn't throughout the fall. And you see that at the very end of the season, just past November 22nd, is the graph drops off. That's actually a soil moisture sensor error from when the ground starts to freeze. So I just wanted to include that. So if you're measuring soil moisture, some sensors do get sensitive when the ground temperature drops below a certain temperature, and you'll see your data looking like it's getting dry. It's actually not dry. It's just the ground's frozen, the water's frozen. It can't measure the water. Another thing I want to highlight in this graph is the majority of the season, our data stay between about 10 and 100 kPa water potential. Where I replicated this trial down in Dickinson in the southwest, a little bit further, drier regime. And you can notice this data, most of the data stays between 150 and 254 water potential. So this graph is set up the same way, but on the right y-axis, the rainfall, we don't get any events above 0.2. We have a few more events. They did plant their cover crop a little bit sooner, so looking at the x-axis on the bottom, starting September 2024, all the way to November 17th. They planted the cover crops, and so, but you can see there's no difference between the cereal rye and the bare ground. So both locations we have no differences. It was a little bit drier in Dickinson overall, but that's the only comparison. And so what does this mean with low available water? In both sites being dry, no cover crop grew above the ground, but this also means the seeds are sitting there waiting for the springtime. So here's a picture of the field here. So spring wheat this year, next year it'll be soybeans, and so we were using a cereal rye cover crop through the winter. It hasn't grown any, but we're getting that snow cover, we're getting that soil moisture we need to actually get the seeds to actually imbibe the water. If the water moves into the seeds, it actually cracks the seeds open and they'll grow, but they won't do that until that snow melts in the springtime. So looking at a little bit of forage data from Minot, so this is done from when you have oats or whatever you were growing, and they come off. Ours came off pretty early because they were used for forage. So mid-August, so that would be similar to like a winter wheat harvest out here. You could actually have your cash crop off, and then you can get your cover crop down. So the reason why I measured in there because we were going to camelina to set up next year's cash crop of soybean. And so harvesting a little bit earlier, we got the cover crop out a little bit earlier so we could take advantage of some of the fall rains. And so this graph is set up the same way. We're going from August 19th, which is right after the cover crop was planted, to November 21st, same time. But on the right side, you could see the rainfall is a lot higher because we had a large rainfall event in mid-September. There you see around the September 15th on this graph is labeled, but it occurred on the 16th. And so the water potential, we stayed pretty high, and then you can see the graph followed throughout. But no matter, so the alley, you can think about as the bare ground plot, and then the green is where you're going from your oats to your camelina. So you can think about your soil health pro plot where you're keeping the ground cover, you're keeping that living root, and being in a no-till system. And so after a big rainfall on that September 15th, 16th, you can see all the soil moisture, no matter regardless of the treatment, went up. But what you notice is after the rainfall, the soil moisture stayed a little bit higher, closer to the top, and where we had cover cropping, compared to the bare ground. Where the bare ground went up with it in the rain, but then it dropped down lower. So this is a good indication of that you're increasing the water holding and then altering the soil structure and allowing more water in and then holding the water longer. Now, yes, we do have that camelina growing, so that cover crop is taking a little bit of soil moisture towards the end of the season, but then it starts responding to some rainfall events towards the end, and it's more responsive and allowing more water to come in. And so our camelina was growing, it was drying the soil down, but it was not taking it out of that range that we see for optimal production. So soil structure is impacted by the biology. So the microbes build aggregates with organic matter, which builds the soil structure. So how do you build the microbes and how do you know you are? So like I mentioned, you can measure them through PLFAs, POC, and different methods like that. Organic matter is another great way to measure, as this kind of connects back to organisms and roots and living items in the soil. And so soil structure is impacted by chemistry. And so like that core I was showing earlier, so here's the zoomed in part of that core with the red circle on the lower right-hand side. So the little white dots in there is actually salt buildups from acidicity impacting the structure. So the bulk density was actually increasing in that area from the high levels of acidicity, which was causing the pore space to reduce. Salinity can also cause issues in fields and lower production. This can also impact the change in structure with a crust on the soil surface and limited water movement into the soil. And eventually, if it gets bad enough, the salinity level, you can actually create a columnar structure and limited water movement into the soil and then through the soil profile if it does get in. So some strategies to improve soil structure. So like Brady was talking about different tillage methods and tillage not affecting the yields as much. So reducing your tillage, or if you need to do some tillage because you got some rut areas or different issues, you can do strip tillage, but try not to leave the ground uncovered for long. Kind of the same message that he had. I have the same message. Try not to keep it uncovered for long, and then limit when soil moisture is high. And so cover crops is one way to do this, and they had great biological associations. So some of the basic ones you can go through is think about as fall cover cropping, or if you had spring wheat, you can go out there with a light harrow and kind of disturb the soil. That's what was shown in that previous picture, where the light harrow on the spring wheat seeds that fell back out of the combine on the back, they grew up and kind of provide us like free cover cropping. It only cost us running the harrow across the field. Intercropping or broadcasting seed during the season of the soybean, which is some of the data I'm going to get into next, is another way. Or summer or full season cover crops with soybeans in the forage as a mix. It can be a great benefit. And that's what some of the other data was shown earlier. So this trial here that I'm showing data from is from Dr. Bortolone here in Minot, North Dakota in 2023. And so he had soybeans growing. He broadcast different cover crops at different timings. And so we're not going to get too deep into it, but just looking primarily at the left at Minot, and there's also Hettinger and Dickinson. The soybean yields were not impacted by him broadcasting cover crops out there. And so a lot of times people are like, oh, you didn't get any yield impact from your cover crops. You probably didn't have much cover cropping. Well, here in Minot, we were actually, because we had the higher soil moisture, we got cover crop biomass from a few of the cover crops, especially cereal rye planted at the R2 soybean timing, or cereal rye planted at the R5 timing, or rye and winter canola put out at the R2 soybean growth stage. So these were at that soybean growth stage. We had little broadcast devices mounted on the back of a sprayer, and we broadcast some seed out the back. So there's no incorporation, just purely laid on top of the soil. We relied on water to actually help get these seeds going, where Hettinger and Dickinson just didn't quite get that rains at the timely point to get the cover crops to grow. And so how much was the soil covered? And so you can see the same ones that had the greater amount of biomass also had greater amount of soil coverage there in Minot. And so a lot of people are like, okay, we got more soil moisture. And so it wasn't impacting my yields. It was getting thing, but wasn't impacting my soil moisture. And so I was presenting a lot of that information. And so here was some soil moisture taken in the fall time. And so this is kind of all compiled together and average. And we see here that cover crops compared to no cover crops, and some of them it's a little bit lower soil moisture, but not statistically different soil moisture lowering. So a lot of times money is the main concern and driving factor of using a cover cropping system. So I highlighted in the red at the top was the return on investment with no cost sharing, and the green box is with cost sharing. So cost sharing, we allocated $30 as kind of an average price of how much you'd get if you were enrolled in a program. So the first column with the no cover crop is $44 in the Minot Narrow. We're just going to look at one here. And then the rye was $419 return on investment. So you lost a little bit of money by going to the rye. But let's move down to the green box. So the Minot Narrow is $444 still because no cost sharing, there's no cover crops. But in the cost sharing at $30, we actually increased our revenue and helped balance that out. So there's many programs out there that can help cover some of that cover crop seed cost and that additional input cost that is associated with going to a cover cropping, and help balance out that equation to help keep the return on investment there. So in summary, here's my last slide. Try something on a small area, like this producer here with having a cover crop of cereal rye and then trying soybeans. They kept the ground covered, they lowered the disturbance of the soil, they kept a living root for more time of the year, and they also increased the biodiversity. But that's important. Just try something on a small area. Don't go too crazy or too big, and try to figure out what works with your system, what you like, and what really works out for you and doesn't hinder you in different ways. Thank you for listening to my presentation. Once again, my name is Chandler, Soil Health Specialist at North Central Research and Extension Center, and I'm a part of the Soil Health team here at NDSU.